This section examines the principles of ignition. The ignition system provides a spark between the spark plug electrodes. The spark must occur at precisely the right time in the engine cycle, and it must have sufficient energy to bridge the gap and ignite the mixture under all operating conditions. The energy required can be obtained from the vehicle's electrical system, but the nominal battery voltage of 12 volts must be increased or stepped up to provide a firing voltage of many thousands of volts. This high firing voltage causes the spark gap to become electrically conductive, enabling an ignition spark to occur. It must have sufficient heat energy to ignite the mixture so that it can continue to burn by itself. Exactly how much energy is required varies according to the condition of the mixture and the pressure in the cylinder at the end of the compression stroke. With an engine at normal operating temperature and under a light load, a mixture with a ratio close to the ideal of 14.7 to 1 ignites readily. However, suddenly depressing the accelerator to increase speed or to maintain speed when hill climbing causes cylinder pressures to rise. This increases the firing voltage needed. The ignition system is designed to have reserve energy available in excess of its normal requirements, so that it's able to produce ignition even when conditions are unfavorable. Most light vehicle ignition systems are of the inductive type. They use an induction coil with primary and secondary windings to step up the nominal 12 volts of the battery to the required firing voltage. The coil operates according to Faraday's law of electromagnetic induction. As the high-tension voltage in the secondary winding builds up, a particular voltage level is reached when the spark plug gap suddenly becomes conductive, allowing the spark to occur. This is known as the plug firing voltage. The level of plug firing voltage depends on many factors, such as the mixture density, turbulence, the pressure in the cylinder, the spark plug gap, the condition of the spark plug electrodes, the resistance of the secondary circuit. When the spark reaches the point where a high-intensity current is flowing in the secondary circuit, the voltage drops to a much lower spark voltage level, sufficient to sustain the spark. This gives the mixture the opportunity to ignite during the duration of the spark. Contact breaker ignition systems provide a simple means of establishing and interrupting the current flowing in the primary ignition circuit. A basic system consists of the battery, to provide a source of energy, the ignition switch, to provide driver control over system operation, an ignition coil, to provide a step-up transformer action, a contact breaker, opened and closed by lobes on the distributor cam as the engine rotates to make and break the primary circuit at the correct time in the cycle, a capacitor, to assist in the rapid collapse of the coil's magnetic field, a distributor, to house the contact breaker and distribute the high tension voltage from the ignition coil and spark plugs to ignite the air-fuel mixture in each cylinder in the correct firing order. Connecting wires and leads suitable for conducting the current flowing in the system at the appropriate voltage level. When these components are connected together, they form two distinct circuits, primary and secondary. In the primary circuit, the positive terminal of the battery is connected to the ignition switch, then to the positive terminal of the ignition coil. A connection is then made from the negative terminal to the contact breaker moving contact point. The fixed contact point is connected to ground at the vehicle frame, as is the negative battery terminal. This allows the circuit to be completed through the frame when current is flowing. A capacitor is connected in parallel with the moving contact and also has a ground connection through its retaining screw. In the secondary circuit, the secondary winding with many thousands of turns of fine enamelled copper wire is wound around a central soft iron core. It is connected internally to the primary winding at one end and at the other to the central output terminal, also called the HT, or high tension terminal. The central coil terminal is then connected by a high tension lead or cable to the center terminal of the distributor cap. A spring-loaded carbon brush connects the terminal to the center of the rotor arm or button. This ensures contact is made with the rotor arm at all times, even when the engine is running. As the rotor arm rotates, it lines up with the segment inside the distributor cap, which leads to the spark plug for that cylinder. With the ignition switched on and the contact breaker closed, current flows from the positive battery terminal through the ignition switch, the primary winding, and the contact breaker to ground, then back to the negative battery terminal. The current flow establishes a magnetic field around the windings. The field is intensified by the rod-shaped laminated iron core. With engine rotation, the lobe on the distributor cam acts on the heel of the moving contact point at the instant ignition is required. This opens the contacts and stops current flow through the primary circuit. This sudden interruption of current flow collapses the magnetic field, and it returns its stored energy to the coil terminals by cutting across the coil windings. This induces a voltage in the primary and secondary winding. Since the secondary winding has about 100 times as many turns as the primary winding, the secondary voltage can also be about 100 times greater than the induced primary voltage. As the high tension voltage builds up across the ends of the secondary winding, a voltage level is reached where the spark plug gap suddenly becomes conductive. A spark then bridges the gap between the rotor and the distributor cap segment, and also the gap between the spark plug electrodes. The secondary circuit is from its connecting point at the primary winding to the spark plug and across its electrodes to ground. From there, it is completed through the battery and primary circuit back to its connecting point. Opening and closing the contact breaker switches the primary current off and on. When the contacts begin to separate, the primary current tends to flow on and produce an arc across the contacts. The capacitor absorbs this surge of inductive current by providing an alternative path in parallel with the opening contacts. The capacitor charges to the peak value of the primary winding voltage. By the time this has occurred, the gap between the contacts is too wide for a spark to discharge between them. This abrupt interruption of the primary circuit assists in the rapid collapse of the magnetic field, and hence an increase in the value of the voltage induced in the primary and secondary windings. As soon as the secondary voltage reaches a value where it bridges the gap across the spark plug, the voltage in the primary circuit falls to a value below that of the charged capacitor. The capacitor then discharges back through the primary circuit, causing further induction, a continuation of the spark at the spark plug, and another charging of the capacitor. Current continues to oscillate in the primary circuit until all the energy in the system is exhausted. This will maintain the spark at the spark plug for about 2 to 3 degrees of crankshaft rotation. Most contact breaker systems incorporate a ballast resistor in the primary circuit. The ballast resistor is inserted in series in the primary circuit between the ignition switch and the positive terminal of the ignition coil. When the engine is running, its resistance provides a voltage drop in the primary circuit, which lowers the voltage applied to the coil. The coil is designed to operate at this lower voltage level and still provide the step-up transformer action needed for secondary circuit operation. However, during cranking, a parallel connection from the starting circuit bypasses the ballast resistor. The voltage available at the battery terminals at this time will now be applied to the positive terminal of the ignition coil. This voltage will give a boost to the current flowing in the primary circuit. The increased current flow strengthens the magnetic field to increase the voltage induced in the primary winding and consequently increase the voltage in the secondary winding. So even under adverse conditions, sufficient ignition energy is available to ignite the air-fuel mixture and start the engine. With the primary circuit being switched on and off repeatedly, each coil has to be designed for a particular application so that it operates efficiently. For a four-stroke four-cylinder engine running at 2,000 RPM, 4,000 sparks must be supplied every minute. The time available to make and break the primary circuit each time is very short. As engine speed rises, the time available is even shorter. It is very important then to ensure that the length of time current flows through the primary winding is sufficient to create the necessary magnetic field. In contact breaker systems, this brief period of time is the period during which the contacts are closed. This is referred to as the dwell angle. It is usually specified in degrees of distributor rotation. This closed period is influenced by the setting of the contact breaker gap. Once this has been set, the angle remains fixed regardless of engine speed. A large gap gives a small dwell angle. A small gap gives a large dwell angle. The manufacturer's recommended gap provides the specified dwell angle for each application, and the recommendations should be followed.